So, as you hopefully have guessed, you would use one conditional variable and one lock to basically solve this issue. Basically, you adding the conditional variable first, adding the lock, making sure that you initialize uh, the system on before, like in the init code, and add a conditional signal. You signal basically once you basically created the thread. In the other thread, you basically try to acquire the lock and you wait for the signal to occur. So basically one conditional variable, one lock, and one state variable, making sure that the initialization occurred. Once the initialization occurred, you can basically proceed. So a large fraction, 97% of non-deadlock bugs studied by Lou are either atomicity or order violations, and these are quite simple to solve. They are just very, very hard to debug. I mean, basically, debugging this can take months, if not years, to get right. Uh, so by carefully thinking about these types of bug patterns, you can, while programming, know that if you're basically programming your system, you should know that I am very prone to fall in these bugs. I'm very prone to add these bugs to my code. So if I think very well, okay, what are the assumptions on order? What are the assumptions on atomicity that I have? This will help you. Okay. Um, there are automated code checking tools that are still not good enough to actually catch all of these bugs, but they are a way that to basically improve your code, basically by running code checking tools. One thing to note is that in the formal methods, in the formal computer science, in the formal programming paradigm, many people are working on basically a way to use formal methods to establish to build your code, and they basically build a whole mathematical model to their algorithms, to their systems, before they actually implement it. There is a wide debate on the efficacy of this, because it takes a lot of time to actually build these models. But recently, people in New South Wales and the University of New South Wales built a fully formally verified operating system. You can actually look it up online. And this formally fully verified operating system is now being used. It's open source actually, and well, it is being used by some military companies in their actual in their submarines, and then in their ballistic missiles and so on. And that is quite interesting because the guys at New South Wales never built it for this purpose, basically. So some bugs are definitely harder than the ones that we saw. Deadlock bugs are very hard to actually find, even because many of the deadlock bugs happen when some order happen. So unless that order happens, you can run for months before you find before this deadlock kicks in. So there are many systems that will run for even years. So you run them for a year, or you run them for 1.5 years, and then every 1.5 years you have to restart your system because all of a sudden your whole system does not work, crashes, does nothing, and it's very hard to reproduce these bugs because it's not like you can check all the conditions that your software can go through easily. Okay, so these are very hard to get. This is basically one example of a deadlock where the order of the lock acquiring the order of acquiring the locks is wrong. So the first thread acquires L1, and then the scheduler decides to run thread 2. The second thread acquires L2, and then tries to acquire L1. It cannot, so it just stays here forever, while the first thread, when it gets scheduled, tries to acquire L2 and cannot because, well, it stays there forever. And these bugs are very notorious because they require the scheduler to kick in at the wrong time, and they require sometimes there can be like deadlock after like 5-10 threads have run, and each one of them acquiring a different lock, and basically you ending up in the deadlock after maybe some very exact order happening in your code. So as the note says, this might occur depending on how the scheduler or when the scheduler kicks in. So how do you deal with deadlocks, or at least try to detect and recover from deadlocks? So the simple deadlocks, of course, these are very simple to solve and to actually spot even. If you basically have, when you're writing your design document or your architectural document for your software, if you basically know that there is locking involved, you should clearly communicate the order of lock grabbing that you will have in your system. Okay. Of course, in very large code bases that are managed between many teams, this can be a bit problematic. So the operating system is a very good example. The virtual memory system, for example, might need access to a file system. It will need access to a file system in order to page in a block from disk, basically to read some data from disk and put it in memory. Or when swapping, for example, you might be swapping into disk, so you're writing to disk from the memory. The file system might subsequently require a page of memory to read the block into and thus contact the virtual memory system. So you might have the case where now the file system now wants to basically update whatever is on the disk, basically reading from memory the same data that was read from the virtual by the virtual memory. So you want to be very careful to avoid deadlocks in these systems, because the file system and the virtual memory system, they are implemented by different people. I mean, the operating system is in general implemented by hundreds, if not thousands of people. Modern operating systems, at least. This applies for both Windows and for Linux. So if you have the people implementing the file system for the new very, very fast, very efficient SSDs, basically not talking to the people who do the virtual memory system for the latest and greatest memory modules, then you will end up in situations where, well, there are deadlocks in things such as even the operating system, where communication between the file system and the virtual memory system is not just important, but it happens maybe hundreds of thousands of times every hour. Okay. Another reason that you get deadlocks is the nature of encapsulation, where we are actually taught not to share our code or to hide details of implementation and provide an interface which basically makes it easier for others to just basically import the library, import some code that you have, reuse it, because they're just going to use your interface, your REST interface, or your API that you're providing them. But if you have locking internally in this system, this makes it very, very hard, because the people using your API might make very wrong assumptions about how your system internally works in terms of locking. So take for example the Java vector class and the method add_all. This is a way to basically you initialize vectors, okay, and you add everything in v2 to v1, okay. because the method needs to be multi-thread safe, because you're going to add multiple elements in a vector together. Locks for both the vector being added to v1 and the parameter v2 need to be acquired. Okay, the routine acquires the locks in some arbitrary order. It can acquire the locks on v1 first and then v2 in order to add the contents of v2 to v1, or it can do it in the other way. If some other thread calls the opposite, v2.add all v1 at nearly the same time, I mean, you're just completely out of luck, okay, and this happens at the same time, you have a potential for deadlocks, because if the first one acquires the lock on v1 first and the second one acquires the lock on v2 first, you're deadlocked. Okay, all of this is basically hidden from the calling application. Now, it's highly unlikely that you're going to have two threads, one of them adding v1 to v2 and v2 to v1, and that these occur at exactly the same time, and so on and so forth. But probability theory tells you that if it could happen, it will happen. Anything that could happen will happen. There is even, I think, a theorem that in probability that is called, I'm not sure if it's the chaos monkey theory or monkey chaos theory, which basically says that if you give monkeys a typewriter and an infinite amount of time, the monkeys will be able to come up eventually. Basically, they're hitting the typewriter for infinity, they'll be able to come up with the entirety of Shakespeare's work out of probability. There is actually calculated probability for that. But then you have to have infinity for them to come up with that. So, and it's proven actually. So anything that can happen will happen. So 4 conditions need to hold for a deadlock to occur. The first one is mutual exclusion. Threads claim exclusive control of resources that they require. A thread grabs a lock, for example. The second one is hold and wait. So once you grab a lock, okay, you do not release that lock. Sorry. You're not going to release that lock if you cannot acquire the second lock. Okay, so you are going to wait for any other locks that you need infinitely. So you hold and wait. No preemption. So you can, there's no way for you to basically shoot down one of the threads or preempt one of the locks. So you cannot forcibly remove a lock from one of the threads that are holding them. And you have a circular wait. There exists a circular chain of threads such that each thread holds one or more resources, such as locks or forks in the dining philosophers, that are being requested by the next thread in the chain. So in the dining philosophers example, your resource, you have a circular wait, everybody waiting for the person on his left or right hand side. If any of these 4 conditions are not met, then deadlock cannot occur. And that basically means that to prevent deadlocks, you need to make sure that these 4 conditions do not occur, and in case a deadlock occurs, then you need to shoot down one of these 4 conditions. So all mechanisms to solve deadlocks in large code bases are basically built on trying to invalidate one of these 4 conditions. Okay, so what the first prevention mechanism is to make sure that there are no circular waits in your system. And this is probably the most practical prevention technique. So you basically draw a resource diagram showing total ordering, showing ordering of what needs to be done. One way to basically enforce the case of no circular waits is to have an enforced total ordering on lock acquisition. Okay, so you have to acquire lock 1 first, lock 2 second, lock 3 third, and so on. So for example, if there are only 2 locks in the system, that's very simple. You basically say that you have to acquire L1 before L2. No one is allowed to acquire L2 before L1. Such strict ordering means that there will no cyclic waits in your system. Hence no deadlocks. Okay, it gets more complicated because it's typically the case that you do not just have two locks, and it's typically the case that different operations require a different set of locks. So sometimes you just go away with partial ordering, basically saying that okay, if I acquire L1, okay, the only to acquire L3 I have to acquire L1 first. To acquire L4 I have to acquire L1 first. To acquire L5 I need to acquire L2 first. Okay, to acquire L7 I need to either acquire L1 and L3 first, L1, L4 and L6 first, L2 and L5 first. Okay, so you try to basically put some order in your system. This is lock ordering as defined in the Linux kernel. This is actually from the file map.c. It's in the memory management module of Linux. And this is basically some order of locking what locks you can acquire, what type of locks you can acquire before other types. Okay. The second one is the hold and wait requirement for deadlocks can be avoided by acquiring all locks at once. So you either basically try to acquire all your locks at once, okay, by first basically sort of not allowing anyone to acquire any locks except after acquiring the prevention lock, okay. So once you acquire the prevention lock, you're just going to acquire all of the remaining locks that you need at the same time. This this global prevention lock means that you have like a global lock on all of your locks. Okay, basically once you acquire the prevention lock, no one else can acquire any locks except for you. It's also again some type of ordering, but it comes at the cost of basically the prevention lock becoming a bottleneck. Okay, so this will again result in a decrease of concurrency in the way that you're doing your parallel programming, because at the end of the day you have a single point, a single contention resource, which is the prevention lock. Okay, and there is an issue here, because if we are saying that you need to call the prevention lock, acquire all your locks at once, and then release the prevention lock, in many cases you do not really know at the beginning of running your method or your function what locks you're going to need, because the locks that you're going to need are highly dependent on what you're going to do in your system. So you have, for example, you might have read-write locks where you're not sure if you're going to be reading or you're going to be writing. So how do you basically do this? So this would require a whole refactorization of your code base to basically know in advance, to not have any uncertainty on what locks you're going to acquire in any function. So one way is basically to kill one of the threads. Okay, so you can have sort of a preemptible thread. Okay, so in this case, for example, some APIs, some programming languages, and some interfaces allow you to do something such as you try a lock. You do not lock a lock, you just try a lock. Okay, so you acquire it, you have it now, but if you end up not waiting on any of the other locks, you're just going to unlock. So in this case, you acquire a lock 1, and then when you try the second lock 2, if lock 2 is already taken, then you basically unlock lock 1 and loop here until you're able to acquire all the locks that you need. Okay, so try lock is sort of, if you can acquire the lock, you take it, otherwise unlock the other locks. And this can lead now to new problems, which is the live lock. We actually discussed this in one of the discussions. It is basically possible that two threads could both be repeatedly attempting this sequence. None of them ever able to acquire both locks, because for some weird reason, for some weird probability, they both occur. They both run this locking in the same order at the same time, and basically the operating system schedules them like in some alternation that results in a live lock. Both of them never ever acquiring L1 and L2. So you can think of ideas to reduce this problem. Basically, one of them would be to add some, for example, some random weight after you acquire lock. Okay, I mean, there are ways to do that. The final one is the final prevention technique would be to avoid the need for mutual exclusion at all. In general, this is quite difficult because the code we wish to run has some critical sections, and if you have critical sections, then by definition you need mutual exclusion. So what can you do? You can do things such as atomic instructions, like the compare and swap instructions, which are atomic basically, right? So there are some atomic instructions that many operating systems, many architectures provide, like atomic increment, for example. And if you basically do an atomic increment, then instead of acquiring a lock, doing the update, and then releasing, you can just call atomic increment, which will update the value to the new amount and uses the compare and swap to do so. Okay, so you can use some of the atomic instructions to implement some new atomic instructions. So you can use compare and swap to do an atomic increment, but also you can implement them in the architecture. So you can have the architecture supporting some atomic instructions. So the x86, for example, it's a complex instruction set architecture, which basically means that it has lots of these atomic instructions implemented already in the hardware. Okay, this is again an insert using for linked list, for example. Okay, again, if you're doing insert for a linked list, multiple threads are trying to insert it at the same time, you can encounter a race condition. So one way to do that would be to add locks in the traditional method, like here. Okay, or you can use the compare and swap atomic instruction like this. So I mean, you can basically either use traditional locking and unlocking mechanisms, okay, or something like this, where the compare and swap is being used to actually force an atomic set of instructions to run together. Okay, so this is basically these are slides from a Berkeley lecture that I really liked, so I thought that we can basically go through them. Some of them are repetitions over the previous slides, but yeah. So now from a completely software architecture point of view, big projects require more than one person or long time basically, so it's usually that you have parallelism. It's very hard to make software project teams work because these are people fight, people quarrel, people fall in love, people fall in hate, and it's just a mess. Okay, if you compare software systems to construction projects, the Empire State Building took 1 year to be built, and the iron production was done thousands of miles away. Still, I mean, the Empire State Building is a building that still exists, right? The Hoover Dam they actually built towns to hold workers for building the Hoover Dam. Still, they were able to finish it in a time that is way less than the Linux kernel time span. So the Linux kernel has been in development for years and for now decades, right? So if you look at the magnitude of software projects, people do not understand that software projects are now much larger than projects such as the building the Empire State Building or the Hoover Dam. And you will be part of some of these projects. I mean, when you graduate, you will be part of some of these projects. Um, when you are doing a big project, it's very hard to do time estimations. I mean, I can see it very hard even on the small projects, looking at the progress with the operating system projects that we have, where you actually have very clear instructions, knowing what is being done. I mean, this is the clearest instructions you can get, basically. I mean, you're getting code stubs, or you're getting links to people implementing similar projects. So basically, if you're looking at the complexity of like real projects, when basically we start, you go and work for GE, General Electric, and they tell you that, you know what, we need to come up with a new operating system for our power distribution, for our smart grid system. And then, well, I don't know what smart grids are. I don't know what is involved. What are the hardware architectures that are being used, or do they have DSPs? Do they have GPUs? What is the hardware that I'm going to run on? I don't know what the distribution is, and I know nothing about power factors and power distribution. So being a software engineer, you're just thrown into one of these projects, just very well paid for doing that. But still, you get thrown into one of these, let's build the operating system for the smart grid. You need to learn what smart grid is. You need to learn what are the hardware, what are the different hardware modules that are being enforced upon you. But you also need to know, for example, if you can maybe add some hardware here, some hardware there. I want an x86 processor here. I want an ARM processor there. I mean, these are all design decisions that you're going to sit and do. Okay, so you cannot even estimate how long it will take you to learn about the smart grids. Okay, you cannot estimate how long it will take your software engineers if you're in a leadership position. You cannot estimate how long it will take your minions, your smaller, your younger software engineers to learn about what smart grid is. So time work estimation is hard. We are eternal optimists, optimistics. So you're most people. I mean, you tell most people, yeah, you know what? How long will this take you? It will only take me 2 days, and then it takes months. Okay, and this is why Colin, every time he sends he posts one of these assignments, he sends you emails asking you to basically start project early. It's going to be hard, because otherwise it gets hard on us and it gets hard on you. Can a project be efficiently partitioned? Sometimes people have a very hard time on understanding, okay, how do I partition this project? So for a smart grids operating system, do I have people working on the power distribution unit software? Do I have people mostly working on the central system? I mean, what do I do? How do I partition this project, especially in a domain that I really know nothing about? Partitionable task decreases in time as you add people. So the more I have people in a project, the harder it gets to actually divide things. People tend to require I mean, people usually tend to think that if you throw a larger number of people at a project, then the project will be faster. This is usually not the case. If especially you require communication between the different partition modules, then you have time for communication. Teams will misunderstand each other. You have all sorts of issues. With complex interaction, time increases, and it does not increase linearly, it increases super linearly. Okay, there's the mythical person month problem. I don't know if you have read that essay. You should actually look for it. where you estimate how long a project will take. When it starts to fall behind, you throw more people to it. Starts to fall behind more, you throw even more people to it, and then the time required takes more time. People usually say that it takes 9 months to deliver a baby, and having 9 women does not help you in delivering the baby faster in a month, right? It will still take the 9 months to deliver the baby. Um, when you add more people, though, I mean, if you add 9 women in the same room, well, it will still take 9 months to deliver the baby. But in software systems, in engineering projects, this is not the case. If you add more people, it will take, maybe if it was like a 9 month project, it might take 18 months instead. So how do you partition tasks? First, you basically do functional partitioning. Person A implements the threads. Person B implements the semaphores. Person C implements the locks, and you end up in deadlocks, of course. Okay. Of course, there are also changes that require others to make changes. If you change the API because, well, I realized that my API doesn't work, so the others need to change whatever code they have. This is actually a real story where a large airline company spent 200 million on a new scheduling and booking system. Okay, two teams working together after 2 years went to merge the software and they failed. Interfaces has changed, documented. They wrote, I mean, when they changed the interfaces, they did document it, but no one noticed from the other team, and the result would cost another 200 million to actually fix whatever crap they ended up with. So the project ended up late in time and costing double the amount of money that was needed. This is a real story. So there is another way to partition tasks, which is basically person A makes the design, person B writes the code, and person C writes tests. Maybe be difficult to find the right balance. Okay. But it's typically, I mean, in software projects, you want to basically know, okay, this person is super good in algorithms. He's not as efficient in programming. He's super good in coming up with algorithms. But that person is not really good algorithms guy, but he's a super good systems hacker. So I mean, how do you basically put your people on who designs, who writes code, and who tests? As debugging is hard, so people usually underestimate the amount of time they need to do testing and the amount of effort that is needed. But to give you an example, Microsoft has 2 testers for each programmer. So one person writing code, 2 people checking his code after him. So you get the idea. Let us look at some different language synchronization support. We have been looking at C mostly. You have pretty straightforward synchronization, the lock.acquire, lock.release, and so on. Okay, but you want to watch out for things such as jump commands and long jump commands that can cause a non-local jump out of a procedure. Okay, in this example, procedure E calls long jump, okay, popping stack back to procedure B. If procedure C has lock.acquire, you have a problem. Okay, so if you have basically jumping between long jumps between different procedures, you can end up with issues because, well, you know, B will call C, C has the lock acquired and tries to acquire the lock, but E has already acquired the lock, but it jumped back, and these sorts of things. Okay, C++ language supports for synchronization. In languages with exceptions like C++ and Java, it's very easy to make a non-local exit without releasing a lock. You basically quit, okay, you return due to an exception, but you never release the lock. Okay, so you void do foo and you call do foo, okay, here, and you run, you cause an exception, and you never release the lock when handling the exception, basically. Okay, so you need to handle the exceptions in the you need to release the locks in the error exceptions, basically. Okay, in the catch. So try catch, you want to basically catch the exception and do a lock release and then rethrow the error. Java language supports for synchronization. You might know that Java has an explicit support for threads and thread synchronization, where you use the synchronized method. Okay. Sorry, the synchronized an identifier for different methods. So here, for example, synchronized will do the synchronization for you, and every object will have an associated lock which gets automatically acquired and released on entry and exit from a synchronized method. So it kind of helps you with that. Okay. Resources are basically, there are two types of resources. There are the preemptible ones, and then there are non-preemptible ones. So you can preempt the CPU, you can preempt most of the security of the embedded chips that you have in the system. There are non-preemptible ones, which is like the disk space, the plotter, chunk of virtual address space. These are all things that you actually must leave with the thread, or you'll get some garbled data. So you need mutual exclusion for the right to enter a critical section there. You may require exclusive access or may be shareable. So read-only files using read-write locks are typically shareable. Printers are not shareable during the time of printing, so you cannot send two printing commands at the same time. They will be ordered. The printer will enforce ordering on the printing commands, because otherwise the printer will just print garbled data. And as we said, one of the major tasks of an operating system is to manage resources. So it's going to use all the locking mechanisms we have been talking about to fix that. There's the starvation versus deadlock. I mean, we have covered most of this. In starvation, threads wait indefinitely. Okay. In deadlocks, you have the circular waiting. This is sort of a wrap up on what we have been talking about. Deadlock can lead to starvation, but not vice versa. Starvation can end, but does not have to. Deadlock cannot end without external intervention. Conditions for deadlock, we sort of looked at these right now. So these are sort of the same examples that that we have been talking about. In this and this example, again, deadlocks will not always happen. You have to have the exact wrong timing, basically, and so it might be that, for example, in a nuclear power plant, you're not going to leave it for a chance, right? So you want to make sure that your code in that case is very well tested. Every single possible scheduling has been taken care of. Okay. Deadlocks can occur with multiple resources, so you can decompose the problem, and you cannot solve deadlocks for each resource independently, because deadlocks occur because different threads are trying to acquire different multiple resources at the same time. So this is an example where you have a system with 2 disk drives and 2 threads. Each thread needs 2 disk drives to function. So each one thread will want to access the 2 disk drives at the same time. If one picks one of them and the other picks the other one, then you are basically in a tight position. Resource allocation graphs, we actually looked at one of them in one of the problems that we have covered during the discussion classes. This is a way to build it. This is one way. You basically symbol threads by T1 and T2 and so on in circles. You resource types, you can have a resource with a single with a single capacity, like R1 now has only single resource, R2 has 3 of them. Okay, this can be your CPU cycles, your memory space, your IO devices. Each resource type RI has WI instances, which is basically the amount of resources that you have in there. Each thread utilizes a resource as follows: either requests it, uses it, or releases it. So you build a resource allocation graph where your vertices are partitioned into 2 types. V is your vertex, either threads, the set of threads in the system, or resources, the set of resources in the system. Okay, and this is an example of a resource allocation graph. So you have T1, T2, and T3. T1 requires R1, which actually is owned by T2, and basically R3 is splitted between T1 and T2. and so on. Okay. So a request edge is a directed edge from T1 to R, basically trying to acquire a resource. An assignment edge is something from R to to T. Okay. Yeah. So if you look at the first graph, there is no deadlock, but the second graph does have a deadlock because R1, okay, is allocated to T2. T2 requires R2. R2 is allocated to T3. T3 is allocated to sorry, T3 requires R3. R3 is allocated to T2 and T1, and T1 has requests R1. So I mean, there is a cycle. If you follow this, there is a cycle that goes from T1 to R1, from R1 to T2, from T2 to R2, from R2 to T3, from T3 to R3, from R3 to both T2 and T1. Okay. This is an allocation graph with a cycle but no deadlock, although there is a cycle here. But since T2 has what it needs to function, once T2 is done, it will release one of R1. And T4 also has what it needs from R2. Once T4 is done, it will release a resource in R2. And in this case, both T3 and T1 will be able to proceed. So not all cycles are deadlocks. As if you have peripherals that are going to basically release some of the resources, if you have multiple resources and one of the other threads can release a resource, then you do not need to have a deadlock. So there are different methods. One of them to handle a deadlock. One of them is basically to allow deadlocks to happen and then recover, and this requires deadlock detection algorithms. And it will basically forcibly preempt resources and or terminate tasks. Then there is the other way, which is using some formal methods, ensure that the system will never enter a deadlock, need to monitor all lock acquisitions as we have previously discussed. And the third one is ignore the problem and pretend that deadlocks never occur in the system. This is actually the way that most operating systems operate. They basically say that, okay, deadlocks will never occur. If they occur, then you file a bug report, and then the bug report will be handled. And this is why basically you get like hundreds of Windows system updates every week, as people file all sorts of reports when a deadlock happens. For a deadlock detection algorithm, only one of each type of resource. I mean, that means that all resources are being consumed. You look for loops. Here, for example, we said that there is no deadlock because eventually when T2 and T4 release the resources, then T3 can acquire the resource and T1 can acquire R1. So in this case, they're having multiple resources have helped you. Okay, this is a more general deadlock detection algorithm where basically you have a representation of all your free resources, you have a representation of all the requests in your system, and you have a representation of all the allocations in the system, all as vectors. Okay, and then you make sure so your available resources is equal to the number of free resources. You add all the different nodes to unfinished and check if any of the nodes / all of the nodes will eventually finish. Okay, so you basically do an iteration for each node that isn't unfinished, checking if requests are less than what is available. Otherwise, you basically check if you loop through them until you basically have the on left nodes in unfinished. Okay, because you remove any node that will finish from unfinished, and these are the ones that are potentially deadlocked. So ways to terminate a deadlock. One of them is again to forcefully release some of the resources. It's not always possible because you might end up with inconsistency, especially if this is an important thread that you end up killing. You can preempt resources without killing off the thread, taking off away resources from a thread temporarily, banning it from using it for a while. Does not always fit with the semantics of your computation system. You can roll back actions of deadlocked threads, okay, and hope that your deadlock will not happen again. So you basically roll back to a state where you did not have a deadlock, okay, and hope that the system will not enter the deadlock again because the scheduler will not schedule it in the same order, okay. Many other operating systems use other options. And now the final slide is basically an algorithm that I want you guys to read. It's called the Banker algorithm, okay, and it's a way to resolve deadlocks. And I'm going to put a question in the next exam on this algorithm. I just want you guys to be able to read something, understand it, come back to me with questions, okay? But this is a question that I will put in the final exam, a question on the Banker algorithm, so that you guys can learn about some of these algorithms and basically take a step towards learning on your own. Thank you, and sorry for the very long lecture.